my computer then. So hopefully, if anyone wanted, I will post it on Canvas or something like that. Okay. Okay. So that's the question. Let's look at the questions we have, which is on exam 3, the number 7. This is question 7. The problem is to find upper bound of the error of the following integral by using trapezoid rule. Okay. So that's a question. Oh, I'm going to post this if that's the case. So yeah, I'm going to post the video if you want. I'm recording it and I'm going to post it if you need that. Okay. So here's the question. We want to find the upper bound of the error of this using trapezoid rule. But before we answer this question, let me give you a simpler example, which is how do we actually use trapezoid rule? So let me start with a simpler question. So example. Suppose I want to evaluate from 0 to 1 of 1 over x dx using trapezoid rule for the case of n equals to, let's say, 4. What should I be doing in this case? So here n stands for the number of intervals. I'm dividing the interval 0, 1, 2. So for example, in this case, if this is the interval, this is 0, this is 1. So I'm dividing this into 4 equal pieces. So the first one will be 1 over 4 and 1/2 and 3 over 4. Okay. So to do the trapezoid rule correctly, we will have to evaluate the following, which is to so what's the formula? You guys have know the formula, right? So it's given by the following equation. For the very first starting points, endpoints is only counted by ones, but everything else will be doubled. So in this case, the integral approximately equals to 1 over 8, which is half of the interval's length, the smaller pieces length. And then you have 0, which is counted once. I mean, sorry, not 0, but f0 plus 2, f at 1 over 4 plus 2, f at 1 over 2 plus 2, f at 3 over 4, and plus f1, and that's it. Okay. Sorry, let me move it upward. So that's a formula for computing this. Here, f refers to this function here, 1 over x, which is my fx. Okay, so give an integral. There's an integrand, which is a function. And to approximate that, we find the function specific values at given different points according to the n that we are looking at. So in this case, n equals to 4. So we are dividing interval 0 to 1 into 4 pieces. And to compute the approximation, we use this formula here, which is for the trapezoid rule. Okay, and then the remaining thing is to compute each point's value. For example, in this case, I choose very wrong number. For example, maybe I shouldn't choose 0 to 1, but 1 to 2, I guess, because 0 doesn't make any sense. So if this is 1, so this is 4 over 5. This is 1 plus that, 1 plus that. This is 2. So everything should be shifted by 1. So this is 7, this is 2. Okay, so that's the correct formula I should be using instead of using 0 to 1, which is improper integration. So in this case, the function should be evaluated 1 over 1 plus 2 times 1 over 1 plus 4 plus 2, 1 over 3 over 2 plus 2 times 1 over 7 over 4 plus 1 over 2. And that's how you find approximation of this given integral using trapezoid rule. Okay, so once we know how to do the integral using approximation by trapezoid rule, the question then is, how good is such approximation? Because we know any approximation will is not going to be perfect. There's going to be some discrepancy because of the scheme we are using. It's kind of approximation. So there's an error between it, which is the distance between the approximation to the true value of this integral here. Because in our case, you can actually compute the true value of this, which will be log 2 in this case. And what we are doing here is to approximate log 2 by this rational expression here. Okay. So then the question is, how do we actually find errors? The formula for that is given by the following expression. Is given by e to the t. E stands for error, t stands for trapezoid rule. The absolute value of that is bounded by k times b minus a cubed over 12n squared. Let me explain what's going on here. So a and b are the lower and upper bounds of this integral. So let me write down what's the integral we are trying to evaluate. We are trying to approximate is the following one. We are trying to find approximation of this following integral. A is a lower bound, b is upper bound, fx is integrand, and so n is a number of smaller pieces. We are dividing this interval from a to b. So there are n pieces, and the k here is the following expression. K is a maximum value of the absolute value of the second derivative of fx. Okay, from a to b. Okay, so you can see that from the expression here, what determines the size of error is by three quantities. First of all, how large is your interval overall? What's the distance between b and a is how large your interval will be, right? And that one is cubed. Okay. And then the second part is this quantity k here, which is the second derivatives of which are related to the second derivative of fx. The third quantity is n, which is squared in the denominator, which makes sense because the larger the number of intervals you are cutting the original interval into smaller pieces, your approximation will be, I mean, intuitively speaking, will be better and better, right? So it's quantified by this n squared term. So that means it actually, the error term actually decays quadratically depending on the size, the number of intervals you're cutting this one into. Okay, so that's the two ingredients. So with that said, now let's look at our original question, which is, in this case, we are looking at from 0 to 1, integration 1 plus x squared dx. And in our case, the n we are using is n equals to 10. So let's see, given these two information, how can we find the ET for the trapezoid rule approximation error for this integral here? Okay. So first of all, since n equals to 10, and b and a are given by 0 and 1 respectively, so the only thing remains is to find the k here. So to do that, we have to differentiate fx. So you first have to recognize what's your fx, which is given by this part. The integrand is fx. So what is the first derivative of fx is going to be given by 2 square root 1 plus x squared and the 2x. Okay, which can be simplified into x over root 1 plus x squared. Okay, this is nothing but chain rule applied to this expression. Okay, the 2x is coming from the chain rule part when you differentiate the square root of 1 plus x squared. Okay. So then, because we are interested in the second derivative, we have to differentiate this one more time. And by quotient rule, you can get the following. You get actually the following expression is going to be 1 plus x squared, and it's going to be 1 minus x squared. You will see that, sorry, this one is cubed in the denominator. Okay. So this is actually the, oh, sorry, I didn't see that you have a question.
Uh, yeah. Will
Yeah,
we be going over also improper integrals?
I'll do that later on after
Okay,
the,
because you said
yeah,
okay, no, yeah,
approximation
because
there.
you said yeah, you said you're like going backwards, and I was like,
Yeah,
that's
yeah.
an
So I'm
equal.
going to
Okay,
do
yeah.
the approximation schemes, and we are going to back to improper integrations. Will be a huge topic for today, and then we are going to move on to the integration techniques. Yes.
Okay, got it. Thanks. Yeah.
Yeah, yeah, yeah. Okay. So at this point, we have computed the second derivative. The question is, what is k? K is a value, right? It's just a number. But what you just computed is a function, is a second derivative of a function, which is still a function. So what exactly the relation between this k to the second derivative is we are looking for the maximum value of this expression in between the interval, which is 0 and 1. Okay, so how do we find the maximal value of this expression? Again, we use the basic ideas is that the larger the denominator is, the smaller the fraction is. The smaller the fraction the numerator is, the smaller the fraction is. You can see that for the numerator, the larger x becomes, the smaller the numerator becomes. So you want the numerator to be as large as possible. Also, at the same time, you want the denominator as small as possible, right? So for this to be happening, the best choice for you is when x equals to 0. Does that make sense? Any questions here? So the maximal value is achieved at x equals to 0. Okay. This is because the numerator is a decreasing function and the denominator is an increasing function. For the fraction to be maximized, it's happening at x equals to 0. Okay. So no questions at this point? Okay, perfect. So since that, then that means the k actually is f prime 0 taking f's value. In this case, I don't have to worry about the f's value because everything is positive. But suppose you're given a function where your second derivative may be negative, then you actually have to maximize the absolute value of the function, the second derivative. Okay, but in our case, it's just that. So which equals to 1. Okay. So with that said, then how do we find the error there? Then the error is very easily computed. It's going to be smaller equals to k equals to 1 times b minus a is 1 minus 0 cubed over 12 is a fixed constant. And n in this case is 10 squared. So that means it's going to be 1 over 1200. Okay, so that's, so remember that there's a less or equal to sign, meaning that the error can maximally be 1 over 1200. It doesn't mean that it is actually equal to this. It's just smaller. It's bounded by this number. Okay, that's a philosophy. We won't be able to compute exactly what's the error because if we know that, we know the original equation already. We have an upper bound. What's your error's maximal possible value could be, and that's given by this number here, 1 over 1200. Okay. So any questions about this question problem from the exam 3 review? Okay, if you have questions, you can raise your hand on the participant tab. Okay, perfect. So now we have talked about the trapezoid rule. What I want to remind you is similarly, you should be doing the same for everything about the Simpson's rule and the error estimate for Simpson's rule. Okay, so let me just give you let me just write down what's needed too, and also 1 prime is how to approximate using Simpson's rule. And the 2 prime is how to estimate, how to find the error, how to find upper bound of error. Okay. So for this one, I will be skipping a little bit, and I will give you some exercise afterwards for you to practice on. So I'm going to skip this part right now for the time reason and give you some exercise, and I will also be posting answers to those because these are very basic. So to use the Simpson's rule, you have to use the formula. You have to know the formula. But since you are taking the exam at home, I assume that you can open your textbook and you have the formula with you. The only thing is to understand the error estimates term. Similarly, there's also a k involved, and you have to understand the meaning of the k and how do you compute the k for each integral related to f. Okay, and then that's something you can do on your own once you have the textbook and the formula. Okay, so I'm going to give you some exercise afterwards for this part. Let me just quickly remark the following thing is for Simpson's rule, the number n has to be even. Okay, it must be even to be performed. So when the interval is even, that means the endpoints, the number of points has to be odd. For example, you cut the interval into 2 pieces, you have 3 nodes in between the intervals. Okay, and for example, if you cut the interval into 4 pieces, you have 5 nodes for the interval. And it is because this number that makes the formula make sense. So the pattern is the following. It's always going to be 1, 4, 2, 4, 2, and 4, 1, something like these. Okay. So suppose you have 3 intervals. If n equals to 2, for example, then it's 1, 4, 1. That's a constant multiplication between each. If n equals to 4, it's 1, 4, 2, 4, 1. And you can see how the pattern goes. Okay. These numbers are the coefficients you have to multiply to each f value at the given points. Okay. So with that said, now let's move on to the improper integration, which I think is the most important new concept you have to understand for this coming exam. So let me give you the first example, which is the question number 8. From the exam, okay, which is the following question. Suppose we try to determine if the following integral makes sense or not on the interval x goes to 1 to 5 for x over root x minus 1. Okay. So this is a question. So let me remark is that first, before we do this question, let me remark that for this type of questions, most likely what you will be doing is something called check it by using definitions. So you always check with definitions. So right now, I guess we are not actually at the point to actually teach you how to do it using comparison principle or something like that. But I guess, I mean, we could, in fact. So let me think about how to do this using definition. So first of all, step 1, let me break it into steps so that makes more clear. Step 1 is determine where is your singularity. By singularity, I mean at which point will make this expression makes no sense. I mean, not defined. For example, in this case, of course, this is an improper integration of the second type, meaning that the integrand will blow up at a given point. So in this case, x equals to 1 is the point where this function doesn't make sense, because at x equals to 1, the function x over root 1 x minus 1 actually goes to infinity, positive infinity, right? Because at this point, x goes to root x minus 1 goes to positive infinity. Okay, that's the case. This is the reason. So this is your singularity. Okay, once you have your singularity, the second step is determine in which way are we actually getting to the singularity. So in our case, the singularity is a lower bound, right? So we are approaching to 1 from the right-hand side of interval. So in this case, this is 0, this is 1, this is 5. So the integral actually can be approximated by letting a parameter t goes to 1 from the right-hand side. That makes sense? Okay. So with that said, so step 2 is to write down the definition. A definition. Because this is the improper integrations, we are not going to define it directly. We always define it using limiting values of another integration. In this case, meaning is that from 1 to 5, x over root x minus 1 dx. This one is not defined because 1 is not even, doesn't make sense for this integral, right? So we define it using the following expression. Limit when t goes to 1 from the right-hand side, because following the reason I just said, of integration from t to 5 x root x minus 1 dx. Now this integral actually makes sense because for any t larger than 1, the whole integral actually is a finite value, right? This is going from 5 to t, which is some number larger than 1. Then this actually makes sense. So our job is to find out what's the integral of this one and apply the definition by letting t goes to 1 and see if the limiting value is finite or not. If this expression, if the limiting value of this expression is finite, that means the improper integration is convergent. If it's going to infinity, that means it's divergent. This is something I mentioned right before the spring break, right? A quick introduction to that. Okay, so let's see how do we do this. Now the step 3, once we know what's the stuff we try to evaluate, then the job is to evaluate this expression using our techniques of integration so that this will be an expression of t, so that we can take in limiting value of these. Okay, so our job right now is to find the integration of these involving the parameter t. Okay, just keep in mind that t is a constant, it's not a variable here. Okay, we are not letting t vary at this point. We're just evaluating these from t to 5. The variable is still x. So how do we do this? In this case, I think that the best approach is first to make a substitution because you have x minus 1 in the denominator rather than x. So the thing is, I'm going to make a u substitution. So that's u equals to x minus 1, so du equals to dx. So the expression here becomes, so from here, I know that x equals to u plus 1. Okay, so this expression becomes u plus 1 over square root of u du, because the substitution I choose. Okay, and then similarly, I can change the upper and lower bound, which will be when x equals to t, for u, it becomes t minus 1, right? And for 5, it becomes 4, which is 5 minus 1. Okay, so u plus 1 root u du. Okay. So this one can be further simplified because I can separate the numerator into u and the plus 1. So that becomes 2 integrations. Okay. And which can be further simplified because the u over root u part can be written as t minus 1 for root u du plus t minus 1 for 1 over root u du. Okay, so here's a question you want to think about. Is this integral actually improper or not? Is the integration from 0 to 4, I guess, in this case, root u improper? Is 0 in singularity for root u, right? If you think about this, you will see that the answer is no. Actually, this integral actually makes perfect sense, even when t equals to 1, which is when x equals to 1, because root u doesn't have a singularity at x equals to 0. The integration is well defined there, right? So what's the graph for this one? The graph for root u is nothing but something like this. This is root u. right? It's the area is perfect finite. So there's nothing wrong with the first integral. The problem actually is only happening for the second part. Okay, so we understand the singularity is coming from the second integration here. But still, we are going to compute everything in terms of t here. So integration for the first one is going to give me actually u 3/2 over 3/2 from t minus 1 to 4 plus, this is going to be u to the negative 1/2. So this is u 1/2 over 1/2 from t minus 1 to 4. Okay. Any questions with this computation here? Okay. So let me proceed. So this one actually equals to something like 4√3 3/2 over 3/2 minus t minus 1 3/2 over 3/2 plus another one is 4 1/2 over 1/2 minus t minus 1 1/2 over 1/2. Okay, so this is everything here is actually the answer for is the integrations of this expression of this one from t to 5 is given by this function of t. Okay, now if you look at this closely, all the exponent here is 3/2 and 1/2, so they are all positive. So when that t goes to 1, what happens is there's no singularity. This term and this term both go to 0, right? So the limiting value actually exists. What does this mean is that, so let me start with step 4. So once we have these, step 4 is taking the limit in the definition. Okay, so in this case, is that you take a limit when t goes to 1 from the positive side of the expression 4 3/2 over 3/2 minus t minus 1 3/2 over 3/2 plus 4 1/2 over 1/2 minus t minus 1 1/2 over 1/2. Okay, which actually equals to, because this two term goes to 0. There's no singularity for this. Okay, so because of that, this actually equals to 4 3/2 over 3/2 plus 4 1/2 over 1/2. Okay, so this is finite. Okay, that just means that your integration actually is proper, it's convergent. So this implies the integral is convergent. Okay, that's the conclusion we have. Okay, so let me actually quickly review what's the major steps I have taken here. So the first step is I determine where is my singularity. So in our case, this is an improper integration of the second type, where the singularity is coming from the integrand going to infinity. Okay, but let me give you another example. It could be something like this. It could be integration from 1 to infinity of 1 over x to the 5th power dx, right? So in this case, the integrand doesn't blow up. The problem is that you have a interval which is infinity. So what's the right definition in this case is by letting t goes to infinity accordingly. Okay, so this is the corresponding definition we are going to use if we have integration, improper integration of the first type, where the interval actually is infinity. Okay, so if the singularity is caused by the size of the interval, then we have this definition here. Okay, that's for the first type. The second step in my computation is once we determine which type of singularity we have and where is the singularity, and we write down the definition, which is what I just did. for the first type is given by this expression. So you have to be very careful and you have to understand that improper integrations cannot be evaluated directly. It must be written as a limiting expression, which is something like this. Okay. Only the right-hand side makes sense. The left-hand side doesn't make any sense. It's just an expression. It's just a formal way to say we want to do something. But together, we have to take a limit. Okay. So improper integrations, you should really understand is this is not it's not an expression, it's not a fixed thing. So here the 1 is never going to be achieved. So you should really think about this as a limiting precise of getting you to 1 by the right-hand side. Okay. So once we write down the definition, the third step is to evaluate what's given here. So this part is where the integration techniques comes into. You may be using integration of parts, you may be using trigonometry substitution, you may be using substitution, you may be using any techniques you have learned, but the goal is to find this integral as with value containing the variable t. Okay. Once you have done this, in our case, in this problem, current problem here is just a substitution, okay, with some separation of the numerator. Once you have done the evaluation, the very last step is just taking the value, the limit in the original expression to see if the definition, if the limit is finite, you have a convergent improper integration. Otherwise, you have an improper integration, which is divergent. Okay. Okay. So let me give you another example and of something that we can do. And so that's number 9 of the question. So number 9 of the exam. Let's do this together again. So the question is given by integration from 0 to negative infinity, x squared e to the negative x cubed dx. Okay. Before we even talk about the improper integrations, I mean, let me just cover this part up and imagine we are trying to integrate this expression by itself. Just by the expression itself, you should see that you have x squared here and you have x cubed in the exponent. A hint will be that you're going to use substitution because once you differentiate x cubed, you get x squared coming off by the chain rule, right? So that's the kind of a strategy we have for evaluation of these integrations if we don't have the limiting expression here. But then let's do repeat everything just like before. I mean, first thing is determine what type of these. I mean, this is an improper integration of this first type, which means that it's because the interval we are trying to use is infinite, large. So it's a type 1. So step 1, the singularity is coming. This is type 1 singularity, type 1 improper integration. Integral. Okay. Step 2 is writing down the definition. So in this case, because it's going from 0 to negative infinity, I mean, there's nothing in between makes this expression not well defined. So the only problem is coming from this negative infinity part. So the definition is limiting t goes to negative infinity of 0 to t, and from x squared e to the negative x cubed and dx. Okay, so this is the expression defining these improper integrations. Like I said again, this expression doesn't make sense. It's not well defined. Only this expression is well defined, and this is actually the real meaning of this one. Okay, so knowing how to write down the definition of improper integration is a key for these kind of questions. Once you have that, step 3 is to evaluate this part. So from 0 to t, x squared e to the negative x cubed dx. Like I said, you choose u equals to x cubed. So du equals to 3x squared dx. And that means du over 3 is x squared dx. So then everything becomes the original integration. So with this substitution, this integral equals to from x equals to 0 x equals to t e to the negative u du over 3. Right? Okay. So then how do we keep writing these? So we can move the 1 over 3 outside. So this is 1 over 3 from 0 to, actually 1x equals 0, u is 0, 1x equals to t, u equals to t cubed. And you have e to the minus u du. Okay. So this integration can be written down very carefully. This is going to be e to the minus u with a minus sign here from 0 to t cubed. So this actually is 1 over 3 e to the minus t cubed minus 1. Okay. Any questions so far for this computation? Sorry, I actually have shown that. Okay. So this is the expression we are trying to take a limit of. But to keep in mind that our t is going to negative infinity rather than going to infinity, because the improper integration is going from 0 to negative infinity. Okay. So our t is actually going to negative infinity. So step 4, limit t goes to negative infinity, 1 over 3 e to the minus t cubed minus 1 actually goes to where? When t goes to negative infinity, t cubed goes to negative infinity. Okay, so negative t cubed goes to positive infinity. So this whole thing actually goes to positive infinity. Positive infinity minus 1 is still positive infinity, divided by 3 is still positive infinity. So everything goes to positive infinity. And that makes this integral, improper integration of the first type, divergent. Divergent. Sorry, I mean divergent. Yeah. So that's the answer for this question here. Again, you can see that I'm using definition by checking if this one is convergent or divergent by using the steps. Okay, so you determine what type of improper integration you have and where is the singularity, and write down the definitions, evaluate the expression involved with t, and then letting t goes to the corresponding limiting value. In the previous case, it's going to 1. In this case, it's going to negative infinity. And from the answer of the limiting value, you can see if the expression, if the original integral is divergent or convergent based on the final answer here being finite or infinite. Okay. So any questions so far about improper integrations? If you have questions, you can raise your hand and I'll be able to actually to answer that. Okay. So let me, okay. Okay, that's for the improper integrations, this part. So let me find another example for us to practice on, actually. Let me do this one. Can I ask, I mean, did Dr. Chadwick mention actually the comparison principle in this part of the question?
I don't think so.
You don't think so? Okay, he didn't mention about the comparison principle.
I haven't heard it.
Okay, so in that case, that actually makes everything simple because you don't have to worry about other stuff. So you have to just have to focus on the 4 steps are listed here. Okay. If you read the textbook, there's another different method for determining if the improper integration is convergent or divergent based on comparing it to known integrations. Let me just quickly see what's going on there with that part. So one key answer fact is the following thing. It's from 0 to 1, 1 over x to the p's power dx. So for this one, let's see that if p is,
Oh no, he did do this.
did he do this example?
Yeah, he showed like an example like this in one of his videos.
But did he ever mention about comparison principle in class, actually, do you think?
He never mentioned it, but like he did like an x to the p power in his kind of
Oh, no,
recordings.
no, this, yeah, but this is not comparison principle itself. Something
Oh,
else will be. Let me quickly explain. So there are two things you should understand is the following two types, which will be very important in later on when you learn series and power series and everything else. So the thing is, for the first improper integrations, this is an improper integration of a first type. The singularity is coming from the origin, x equals to 0. The integrand blows up. So in this case, this one is actually finite when p is smaller than 1 and larger than 0, and infinite when p is larger or equals to 1. Okay. So this is the for improper integration of first type, this is the reason. So remember in the previous case, we just did that is 1 over root x integration dx from 0 to 1. And in the exam question, roughly this one is convergent because in this case, what's a p? Is p is given by 1/2. It's actually in between this interval here, right? It's smaller than 1 and larger than 0. So this one is finite. So that's why in this example here, this is convergent. But for the second type, for the second part, this is improper integration of the first type, where the singularity is coming from the infinity part. And in this case, the answer is reversed. This one is infinite when p is smaller or equals to 1, and finite when p is larger than 1. Okay. So you can see that in both cases, p equals to 1 is a cutting case. Okay. And then let me explain a little bit the intuition about this. Is when p is in this range, when p is small, this one actually blows up slower because the larger p is, the denominator is smaller when x is between 0 and 1. Just imagine when x is a really small number, right? When p is, the larger the p is, the smaller the denominator will be. So that's why in this second case, the function blows up faster than the function in the first case. That's the intuition you have. Because this one blows faster, that means it's enclosing larger areas. The larger the area is, the larger possibility is going to diverge, right? Whereas in the second case, the larger the p is, when x is in between 1 and infinity, the larger the p is, the larger the denominator will be. Just imagine x being 2, x being 4, x being 10, then 10 to the second power, 10 to the third power, 10 to the fourth power will be larger and larger, right? So the denominator, the whole thing will be smaller and smaller when p getting larger and larger, right? So this corresponds to faster decay to 0, right? And this corresponding to slower decay to 0. They all goes to 0, but the only one is decaying to 0 faster, that will guarantee this improper integration to be finite. Okay, that's kind of intuition you have. If you don't understand this part of explanation, try to read your textbook to make sure you understand this. This is very important for later on understanding of later on materials. Okay. So once we have these two base case, then the comparison principle is essentially speaking that if we have an integration, for example, this one here. Let me do this. Okay. If we know that, how do we know that this integration will be convergent or not? Suppose this one is bounded by something finite. This will imply that this integration is finite, right? Suppose this one is larger than something which is infinite. This one is convergent. And if this one is something like this is divergent. Okay, that's the So then the thing is, what is this finite or infinite thing you are using? You are comparing this to something that you know, which is converging or diverging. Okay. So for example, in the first case, in this example here, when x is varying between 0 and 4, x plus 4 is varying between 1 and 5, which is finite, nothing wrong with it. So you can see that this is probably 5, this is probably 1. The thing is coming from the denominator, which is root x, right? This is the reason why this is improper integrations. So once we have these, how do we determine if this one is, to which one we are comparing this to, is by noticing that because x plus 1 over root x is smaller equals to 5 over root x, when x is in between 0 and 4, right? In this range, you have this inequality. But we know that from 0 to 4, 5 root x dx equals to 5, 0 to 4, 1 over root x dx is converging, it is finite. Okay. The reason why this is finite is because the p-test I just mentioned. Because in this case, when p is smaller than 1, is converging. So in this case, the p is really just 1/2. Okay. And because this is finite and the integration here, the integrand, original integrand is always smaller than this. So the integration itself, this will imply that integration from 0 to 4, x plus 1 over root x dx is smaller equals to 0 to 4, 5 over root x dx. So that tells you that because this is finite by the p-test, so this one is finite. Okay. This is the reason, this is something called comparison principle. Okay. So basically you are comparing your improper integration to something that you know for sure is convergent or divergent. In our case, it's always the p-test model. It's always 1 over x, the p power that we're using to compare to. But since you guys mentioned that Dr. Chadwick didn't see something about this, so you don't worry about this part. You just follow the steps I give to you guys using the definition to check if an improper integration is convergent or divergent by honestly evaluating an integration itself. So the limitation to the definition method is that you have to know how to integrate, right? That's the key. If you don't know how to integrate the integrand, you are done. You cannot do anything further, right? You have to do the integration correctly to do everything. So that's why in the previous examples, you can see that we have integration of these. We have to actually using some techniques to do the job. And this is where all the integration of techniques are made useful for, right? So you learn all these techniques to do something, right? This is the point. I mean, now you can have something to evaluate. So that's the point, okay? So that's the part for improper integrations, the 2 questions from the review exam. Any questions about these 2 questions from the review exam? Okay. If you have questions, just raise your hand. I will see it and they'll be answer your questions then. Okay. Good. So now let's move on to partial fractions. Actually, that's another topic I want to actually emphasize today. Again, let's look at the exam question, which I want to start with number 6, which is a more complex question.
I have a quick question about
Sure, yeah.
last night's homework.
Yep.
Do you have access to the WebAssign problems?
I don't, but
here, I can pull it up here. Hold on.
Yeah. Maybe I can share your screen or something like that. Or you can just tell me what the expression you have, actually.
Okay, here, let me pull it up.
Yeah.
It was last night's problem 6.
Mm-hmm.
Okay, this is due. Oh. Okay, here we go. Okay, here it is. It's the integral from 1 to 6.
Okay.
Of 1 over x times ln of x to the 0.1 dx.
To the 0.1 dx. Am I right with the expression?
Yep. Yep, exactly.
Okay, so perfect. Let's answer this question first. A good exercise actually to do it. And let's do that. So step 1, determine where the singularity is. When x goes to 0, right? This is actually a very fun question because when x goes to 1, right? So that's a question. Sorry, I didn't see that. It actually goes to 1. It's not going to 0. Make it less fun, actually. Sorry to see that. But anyway, when x goes to 0, it's actually the Lebesgue rule. Actually, you have to worry about. But when x equals to 1, there's nothing to worry about. It's just x goes to 1, log x goes to 0, so singularity is 1, right? That makes sense? So we don't have to do anything. So x equals to 1 is singular. Okay. So step 2, because it's an improper integration of the second type, it's singular at a given point, which is a lower bound. So we write down the definition. The definition is going to be limit when t goes to 1 from the positive side, integration from t to 6, 1 over x log x to the 0.1 dx. Okay, right? That's the definition we are trying to evaluate, which is how we define this improper integrations. We define it using this definition, a limiting expression. Step 3, let's try to evaluate everything inside the before the limiting expression, which is this part. Okay, any suggestions what we should be doing if we want to evaluate this? I mean, you have log x, you have x. Does that ring a bell? That's something we have learned before. And especially this is not x, it's actually 1 over x, right?
So it's integration by parts?
Oh, no, actually not even that. It's
U substitution, I guess.
U substitution, exactly. So you can do U substitution. So that U equals to log x. So du equals to 1 over x dx, right? I guess, right?
Yeah.
Okay, so then the integration becomes when x equals t, u equals to log t. When x equals to 6, this is log 6. 1 over u to the 0.1, right? And then du. That makes sense?
Yeah, makes sense. Makes sense.
Okay. So once we have that, then that means this actually equals to u to the, I guess, how do we get here? Is negative, so 0.9 over 0.9 from log t to log 6, right? Okay, so this actually equals to log 6 to the 0.9's power over 0.9. How do we get 0.9? It's because this is negative 0.1 as the exponent. So you raise it by 1, which gets you here to 0.9. It's just power rule. Okay, so this is actually matters log t to the 0.9 over 0.9. And it doesn't really matter what's the value here, which is 0.9 or 0.8 or 1.5. It doesn't matter. As long as this one is positive, you see that when t goes to 1, this goes to 0, and this is positive, so everything goes to 0, right? So step 4, limit when t goes to 1 plus, because log t goes to 0 plus, right? So this is positive, so everything goes to, so the original expression, t goes to 6 log x to the 0.1 dx goes to log 6 to the 0.9 over 0.9, which is finite. So this tells you that this is actually converging. Okay. Okay, does it make sense? Okay, perfect. So we see another example. How do we do this? And yes, keep in mind that there may be various ways to do the problem. So let me think about one. let me think about one that's involving maybe other different techniques that we have learned for improper integrations. Because sometimes you may have to use substitution, you have to use integration of parts. Let me pull out one example that I want you guys to do, actually. Yeah, how about this one? Actually, yeah, this is a good example here. So before we move on, actually, let's do this one. Let me see, this is another question that you want to actually practice so that you have some familiarity of your stuff. Sorry, I used t rather than x. Let me use x, actually, make it more uniform. Okay. So the integration we are trying to evaluate is from 0 to 1 log x dx. Okay, is that clear? I mean, yeah. So let's first determine where the singularity is. Step 1. When x equals to 1, log x is just 0. It doesn't make any, it makes sense. But when x goes to 0, this actually blows up to -infinity, right? So the singularity is coming from x equals to 0 is singular. Okay. So this is the singular part. So step 2, the definition is limiting value when t goes to 0 from the positive side, right? I mean, because x equals 0 is a singular point. So this actually is going from t to 1 log x dx. Okay, so again, I'm writing down the definition of my improper integrations. So this is the thing I want to evaluate, which equals to that. Step 3 is, then how do we evaluate this? We have expression is the following. Do you guys all recognize these? And how do we evaluate from, don't worry about the t and 1 part. Just think about this being a indefinite integrations. So how do you evaluate log x dx?
Bo, quick question.
Sure.
How do you know when t is approaching 0 from the right or left with these?
Oh, it's because, I mean, your x belongs to 0 to 1, right?
Okay.
Yes, and the x is moving in between these. If a singular point is 0, then you're moving to 0 from the upper side, right?
Right.
So it's the right-hand side, right?
Gotcha.
So let me draw a picture before, I move on to the answer. So this is 0, this is 1. Your t is going to 0 from this side. This is where the singular point is, right?
Right.
Yes. So when t is moving to the singular point, you see that t is always larger than 0. So that makes t goes to 0 from the positive side.
Okay.
Suppose I change the question. Suppose this is 1 over x minus 1 integration from 0 to 1 dx. Okay. The singular point now is no longer 0, right? Because when x equals 0, this makes sense. But when x equals to 1 is a singular point, right?
Mm-hmm.
So then when x goes to 1, you are moving to, the definition of this will be having t going from 0 to, or will be like something like this when t goes to 1 from the minus side, 1 over x minus 1 integration from 1 to t dx. That makes sense?
Yes.
Yeah, because it depends on where your singularity is. If your singularity is the lower bound, you're going to the right-hand side from the right-hand side. If your singularity is on the upper bound, then you're approaching the upper bound from the left-hand side, right? From the lower side.
Okay, I see, yeah.
Yeah. So that's one thing. Okay, so what else? Yeah, let me digress later on, but let me focus on this question here. So do you guys know how to integrate log x dx? Okay. Anyone who doesn't know? Yes, so by parts. Yes, indeed, Brian. So please remember that you don't just have substitution technique on your own. So I will see something later on quickly, but let me just briefly see that. When you have an integration you want to evaluate, you have to be able to determine which technique fits the best for the problem. In this question here, there's no way you can do integration. So given this expression here, this is definitely not partial fraction technique. This is definitely not trigonometry substitution. So that leaves you only two possible choices, U substitution or integration of parts. But suppose you want to do U substitution. This one doesn't have a 1 over x term to help you, like the previous case example, right? So that gives you a hint that you want to do integration of parts, okay? And actually this one works because we remember that we do this problem by the following technique. We imagine this being 1 times log x dx. So here, this is my u, this is my dv. So u equals to log x, dv equals to 1 times dx. So du equals to 1 over x, and v equals to x, right? So this integration now becomes integration from x times the log x minus integration of x times 1 over x dx, which is x log x minus x plus c, right? So this is how we do this problem using integration of parts, okay? Please definitely review on this part. I mean, we have learned so many different techniques, and you have to be able to judge which is the best for your problem at hand, okay? So this is step 3. We know how to evaluate this. This is just equals to x log x minus x from t to 1, right? Which equals to which equals to minus 1 minus t log t minus t, okay? So this is the expression. So let me just keep writing here. So step 4, we take the limit when t goes to, which is the singularity point, is 1, right? 0, sorry. Of negative 1 minus t log t plus t, okay? Let's see what's the limiting value of this expression. When t goes to 0, positive side, this is constant. This goes to negative 1 again. When t goes to 0 from the positive side, this goes to 0. There's nothing to be worried. This one is also proper. The only problem is coming from this t times log t term. Okay. So my question is, what's the limiting value when t goes to 0 of t times log t? Do you guys remember that? So which one decays faster? Log t goes to infinity, but t goes to 0. So this is a 0 times infinity type. Does that ring a bell? Okay. So anyone who knows this answer? Which rule do we use to determine the limiting value of these?
L'Hopital's rule?
Yes. So we do that. Goes to 0. So log t over 1 over t. And this actually equals to limit when t goes to 0, 1 over t squared negative. So equals to limiting t goes to 0, negative t, which essentially goes to 0. So that means from this computation, we know this also goes to 0. Okay. Because L'Hopital's rule with the detail are given here. Okay. That makes sense? Okay, so this is how we compute, how we finish the problem, because we know now the limiting value of this actually goes to negative 1, which is finite. So that means this improper integration, which is singular, is actually finite. So this one actually is convergent. Okay. Did Dr. Chadwick ever actually show some example in class like these?
Can you show the bottom of the where you did L'Hopital's rule again?
Okay, so let me.
And is equal to the limit of 1 over as limit as t goes to 0 of 1 over t over negative 1 over t squared?
Oh no.
What do you have right there?
The value we are taking is actually the expression for the integration, right? Which is this part. So remember that we try to take in limiting value of these, right?
Right.
This
I just
line.
can't. I'm having trouble reading the lower right there.
Lower right is I'm just computing the limiting value of this middle part using the L'Hopital's rule.
Right. Right. So it says you have limit as t goes to 0 of ln of t over
T times
1
log
t.
t equals to limiting t goes to 0, making this into the quotient form, log t over 1 over
Right.
t. Remember this old trick?
Yep.
And then you differentiate, you get 1 over t in the numerator, you get 1 over t squared with a negative sign in the denominator.
Okay.
That's L'Hopital's rule. And then
Right.
simplify that, you get negative t as the overall expression.
Sure. Okay.
And then that goes to 0 when t goes to 0.
Got it. Thank you.
Yep. And then that's how the middle term actually goes to 0.
Got it.
Okay. Does
Could
this
you,
make sense?
show the
Basic?
paper?
Yeah. Question?
Could you like show the whole paper?
Let me actually try to see if I can put everything here.
So it's convergent and the answer is -1?
Yep. But the -1 doesn't matter, actually. I mean, yeah, maybe it matters, but it's better that you know how to do it. Yeah, it's -1, actually. But I'm not quite sure about my computation. I mean, the numerical value could be something changed with a sign there. But anyway, but I think it's -1, actually. Yeah. So Matt, can you see that, the whole thing?
Oh, yeah, thank you.
Yep. Okay, perfect. I didn't do that because I'm writing kind of small here. So yeah, you can take a picture or whatever, zoom in to see the whole thing. So let me explain again the steps here. So step 1 is to determine where is the singularity. Is it because the interval is infinite or because somewhere the function is blowing up? In this case, it's x equals to 0. Write down the definition of the improper integrations. So the more appropriate way to write this is to see that 0 from 1 log x dx actually equals to the limit t goes to 0 positive side from t to 1 log x dx. So this is the more appropriate way to write this. What I'm doing here is just to show you that what our goal is. So our goal is to find the limiting value of this expression here. Okay. So the next step is to determine what this expression is involving t. How does this one depend on t explicitly? Can we integrate that? In our case, we can do that because in this case, we know how to do it using integration of parts. This is the emphasis I want to give to you guys is you don't just have substitution technique at your hand. You also have integration of parts. You also have something else at your hand to help you. For example, let me move on to the next page, sorry. It's something like this. For example, you could have integration example like this. Is you may be having, for example, from 0 to pi over 2 secant x dx. Okay. Can you guys recognize my handwriting? The upper bound is pi over 2, the lower bound is 0. And you have secant x dx. Okay. So where is the singularity? So what is secant x? Secant x is, so how do you define secant x? Is 1 over cosine x, right? Or sine x. Right? And where is the singularity? When x equals to 0, this is 1 over 1. When x equals to pi over 2, this is 1 over 0. So the singularity is coming from x equals to pi over 2. Right? So this is step 1. Right? Step 2 is to write down the definition. So this is actually limiting value. T goes to where? Where the singularity is pi over 2. Because it's the upper bound, you have actually negative, right? You are going to pi over 2 from the lower side. And you have limiting t secant x dx. Okay, this shouldn't be having any trouble with. You shouldn't be having any trouble with this step. The key is for number 3, step 3. How do you evaluate from 0 to t secant x dx? Do you guys remember? This is something I mentioned before the spring break. How do you integrate from 0 to t secant x dx? Does anyone remember? What's the answer for that?
You have to multiply it by its derivative or something, but it's ln of secant x plus
Yeah, that's,
tan x.
remember that? That's a very tricky integrations that we have. It's actually equal to, this actually equals to log secant x plus tangent x. Remember this expression?
Yeah.
From 0 to t. Yeah, so this is actually what we did before the spring break. Is for this particular case, you have to know the answer because you won't be able to derive it on exam. But of course, you have the textbook now. But anyway, yeah, knowing how to do this, I mean, is one thing. And then step 4 is what happens when you take the limit, when t goes to pi over 2 from the lower side, log secant x plus tangent x from 0 to t. This one definitely blows up, right? I mean, because you see that you have log infinity, right, appearing there. So this goes to infinity. So it's divergent, okay. And that's the answer for this question. Okay. So far I've been giving you several examples about how do you apply the definition to determine if improper integration is converging or diverging based on these steps, okay. One last example is the following type, is that you may have a singularity which is embedded in the interval. By that I mean if you have something like these. Okay. Sorry for my handwriting being too small. So actually, yeah, let me write it larger actually.
I'm sorry, just one question real quick.
Yeah, sure.
Why is it divergent again? I missed that part.
Which one?
The last problem.
The previous one. Why is the limit to infinity?
Yeah, I didn't hear that part. I'm sorry.
Oh yeah. So let me do that again quickly. So when you see that the expression here involves log secant t plus tangent t, essentially speaking, right? The other part is log secant 0 plus tangent 0, which is finite, right?
Yeah.
So the only thing is you have to determine if this expression, log secant t plus tangent t, has a limit or not when t goes to pi over 2, right? But when t goes to pi over 2, where does tangent t go? It's going to positive infinity. Where does secant t go to? It's going to positive infinity. So what happens when you add to positive infinity in the absolute value sign is positive infinity, right?
Yeah.
So what is log of positive infinity? Is infinity, right? So that's how you get these.
Okay, gotcha.
Yep.
Thank you.
Yep. So let me come back to the question I want to do, is this one. For this one, I won't be determining the answer, but I will give you some explanation, some remarks. Is now where is the singularity for this? So step 1, where is the singularity? It's clear, x equals to 1, right? It's the singularity. Right, x equals to 1 is singular, but x equals to 1 is not the lower bound, nor it's the upper bound, right? It's actually in between. So let me draw the picture here. You have 0, you have 5, you have 1, which is singular. So this is the singular point. Now, how do you determine if this one is converging or diverging? You actually break this one into 2 pieces. Let me see, what does this mean? So actually this one, in this case, the integration should be broken into 2 pieces. It's actually limit when t goes to 1 from the positive side of 0 to t, 1 over x minus 1, 1 over 3 dx, plus limit when t goes to 1 negative from t and 5, x minus 1, 1 over 3 dx. You guys follow that? If your singular point is in the middle of your interval, then you break your improper integrations into 2 parts. The part that involves this part and the part involving this part alone, okay? But now how do we see that this one is converging or not? It is converging for this only when both limiting value is finite. Keep in mind, if one of them is blowing up, diverging to infinity, this will be diverging. Okay, that makes sense? So for this to be converging, let me see that again. You want both integrations, the limiting expression, to be finite to be converging. Okay. So that's how we do a problem like this. And then everything else is just the same. And you follow the steps, you will see that actually this one is converging because roughly speaking, by the p-test, this one has a p to be 1/3, which is smaller than 1, and making it converging there. Okay, so let me just quickly remark that in this case, p equals to 3, hence it's converging. I will leave this as to you guys for you to determine, because this is actually something very similar to what I did before. Okay. Okay, any questions so far for this whole thing about improper integrations? Okay, so yeah. So with that said, now next thing is we are going to move on to, sorry?
Oh, I was just asking, like, your limit t approaches 1, like, from the right. So, like, your upper
Oh, sorry, I
bound-
mean, there's some sign problem, I guess. So this one is from t negative, this is from t positive. Yep.
Okay, thank you.
Yep, thanks. Yep, it's going to, yeah, that makes more sense then. Okay, any other questions before I move on to partial fractions? Okay, so I'll consider you guys understanding the steps I've been listing, because I've been repeating this like 4 times, so you should be having a sense of what to do actually. I think that Dr. Chadwick must have teach you guys also very properly in the same way actually. So let me do the improper integrations, the partial fractions. Okay. So the partial fraction, the first thing I want to emphasize is for partial fraction, what you need to do. So for partial fraction, you have to know how to do long division. Okay, and you have to know how to find the right template. How to factorize, I guess, that's another thing. Your denominator. Number 3 is how to find the right template. Number 4 is you have to be able to actually to find the constant, solve the system for the constant, solve for the constant. Essentially, these are the steps you want to follow actually. Solve for the constants. Number 5 is to integrate. Especially when there are quadratic involved. A quadratic expression in the denominator. This is where the completion of square is coming into the picture. Okay, so these are the basic 5 aspects you want to understand for partial fractions. Okay. So yeah, let me actually do it one by one. I think that I sent you guys actually a worksheet from last time, together with the answer for the previous one. So in that one, there's an example question, which let me take it out. It's the following one. Have you guys read the example 2? I'll give it to you guys. I would take that as a no. Okay.
Wait, which example?
Remember that I sent out a solution to worksheet 8.4.
Okay.
In the last 2 pages, there's example 2 I contend. But anyway, I mean, I'm going to do it now, actually. You can see that. I just try to illustrate the first point is if we have the following. Suppose you are given a question like this. Okay. Suppose this is the question we are looking at. Okay. We try to figure out how do we integrate this expression here using partial fraction? Because I mean, there's no other way you can do it. This is a typical question from partial fraction. You have polynomial in the denominator, you have polynomial in the numerator. So essentially, that's the only technique we have besides substitution, if that's not easy to see. And how do we do this problem here is we actually, so let's see how these points make sense. So from number 1, do we need to do long division? In this case, the degree of the numerator is 3, and the degree of the denominator is 2. That means you have to do long division. Even if you have a degree 2 polynomial in the denominator, you still have to do long division. The point is to make your numerator at least 1 degree smaller than your denominator. That makes sense? Okay. So in this case, how do we do the long division? We do it just like dividing integers. Okay. I think that we did something similar in class actually at one point, but let me do this carefully. So we try to divide the numerator by x squared minus 3x plus 2. So roughly this is analogous to 9/4. How do we divide these? We write 9 in the square root. We have 4 outside. And how do we divide that? We have 2 copies of 4, at least making it 8, and the remaining term is given by 1. That makes sense? So what this is saying is that 9 equals to 2 times 4 plus 1. Okay. This is just a very naive model that you want to keep in your mind. Dividing by polynomial is the same. So now with that said, how do we divide this polynomial? We have 3x cubed minus 8x squared plus 4x minus 1 divided by x squared minus 3x plus 2. Okay. So let's determine. So we have x cubed in here, and we have a constant 3, and we have x squared here. So to cancel out the first leading term, which term should be multiplied to the denominator? Is given by 3x. That makes sense? If you multiply this by 3x, this term by 3x, you get 3x cubed minus 9x squared plus 6x, right? You're measuring every term by term. The reason why we choose 3x is that now the first leading term got canceled out when you subtract. So you get minus 8x squared minus 9x squared becomes x squared. Minus becomes positive, okay? And 4x minus 6x is negative 2x, and you have a minus 1, right? Okay, so next step, we try to cancel out these. And this is x squared, and we have x squared. So all we need is just 1 copy of that, so which is 1. So that gives you x squared minus 3x plus 2. And you do the same subtraction again. So this gives you x minus 3 as the remaining term. Now this one is degree 1, right? So you don't have to do any long division further. That's it. That's the end of the long division. So we have it. And now how do we actually evaluate this? We can write this as 3x cubed minus 8x squared plus 4x minus 1 actually equals to 3x plus 1 times x squared minus 3x plus 2 plus x minus 3, right? So this is the remaining term. This is the other part, right? Just like the previous case with the integers. Does that make sense for everyone? How do we get here? Okay, so now let's move on to step 2. Once we have the long division, now how do we factorize the denominator? Step 2. The denominator is x squared minus 3x plus 2, which is a quadratic. Luckily, in our case, we have this one to be x minus 1 times x minus 2, right? Because 1 and 2 are the 2 different roots for this polynomial, right? So that's why you get this factorization here. And the thing here is that you have two linear pieces. Okay, so once we have that, now let's determine step 3. So now we have the long division, we have the factorization. So let's do everything together. So 3x cubed minus 8x squared plus 4x minus 1 over x squared minus 3x plus 2 actually equals to 3x plus 1 times x squared minus 3x plus 2 plus x minus 3 over x squared minus 3x plus 2, right? Now that's the reason why we do long division, because for the first term, this cancels out, you are left with 3x plus 1 plus x minus 3, x squared minus 3x plus 2, right? So integration of this part of this expression is the same as integration of this part, which is a polynomial, which are very easy to be attacked, together with integration of this smaller piece, the other piece, where we are going to apply partial fraction to these. Okay, we're not going to apply partial fraction directly to everything here. It is to this part we apply partial fraction technique. Okay, so let's move on to that, to the next step. So next step is to determine what is the right template. So let me write in this. So now let me mention that we are interested in this. Okay. The problem is that this one is easy. So I'm going to skip this. But don't forget that when you do the problem on your own, don't forget about this part if you have a long division. Now let's focus on this part. This is where we do partial fraction. Okay, after long division. So now we do it by the step 2, we do the factorization. So this actually equals to x minus 3, x minus 1 times x minus 2 dx, right? So this actually equals to, by partial fraction, because these are two linear pieces in the denominator, so we have a over x minus 1 plus b x minus 2 dx as the red template, because each of these are linear pieces. Okay. So how do we evaluate this? We have to know what a and b are, right? I mean, this is one of the questions. So step 4, solve for the constant. And how do we do that? We make these two equal, right? We want this to be equal. And to do that, there are basically two different approaches. I've written it in my answer to solutions to worksheet 8.4. I've been talking about that a little bit in the answer. So the first method to do this is by, first of all, you always do the cross multiplication to simplify, to make them into the same denominator. So in this case, you have a x minus 2 plus b x minus 1 over x minus 1 x minus 2 equals to x minus 3 equals to x minus 1 times x minus 2, right? You always make it into something like this. Because they have the same denominator, essentially you want the numerator to be equal to each other, right? And then there are two ways to do this problem. So the first approach, which will be based on simplifying the right-hand side, because the left-hand side, because you're collecting the constant terms, you're collecting the terms involving x. So you get a plus b x plus minus 2a minus b equals to x minus 3, right? This is what you get when you're collecting terms, similar terms, into groups. You collect linear terms, you're collecting constant terms, and these should equal to the right-hand side. So that makes that a plus b should equal to 1 if you want them to be equal, because the only term on the right side involving x is 1 times x, right? And the only constant on the right-hand side is -3, so you want minus 2a minus b equals to minus 3. And then you solve for the system, right? The standard way for doing this is by substituting a in terms of b and put that into the second equation, you can solve for that. Okay, so this means that b equals to 1 minus a, so minus 2a minus 1 minus a equals to minus 3. Then you can solve for that, right? I guess in this case, that gives you that a equals to 2, and actually, let me see. And b equals to -1, right? You can solve for that. Okay, so this is the first approach by collecting terms, similar terms, and equating their coefficients. I believe that Dr. Chadwick must have taught you guys in this way in class. The only disadvantage of this method is that when you have more terms than just linear terms, this is a very simple example. But if you have complicated examples, this expression, this equation you are writing down may involving more constants. For example, you could have a C, you could have a D. In that case, you have a very large systems to be solved for. And that's very bad because in that case, you have a larger system to be solving for and you have to do it very carefully. So let me show you a different way for doing this. Is we know that we want a times x minus 2 plus b times x minus 1 equal to x minus 3, okay? This is the equation of two functions, right? The right-hand side is function of x. The left-hand side is a function of x involving a and b. Because these two functions are the same, they have to be of the same value at different function values, at different x value, right? So then you take advantage of the left-hand side, noticing that you have x minus 2 and x minus 1 involved. So why don't you just take x equals to 1? If x equals to 1, the left-hand side becomes a times -1 plus b times 0 equals to 1 minus 3 equals to -2. That makes sense? So from there, you can see that you get the equation of a only, which gives you that a equals to 2. You do the same thing for x equals to 2. So you get a times 0 plus b times 2 minus 1 equals to 2 minus 3, tells you that b equals to -1. Okay. Which one do you think is simpler? I mean, in this case, I think both are okay because the first approach doesn't involve too much a computation, but still, in this case, because you have two linear pieces, the second method works better. So this is my suggestion. In your question you will be solving for, suppose that you have a really good factorization of your denominator. The more linear terms you have, the more you want to use the second approach. In some sense, you want to mix these two approaches. Whenever you have a linear factor in your denominator, you want to do this. That's my point. Okay, you want to do the second approach to help you a little bit. Okay, so if you are not quite understanding my explanation here, go to the worksheet. The solutions are sent out to you guys on worksheet 8.4. I have a part explaining how do you mix these two approaches together at one point. Okay, so now we know what a and b is. So the remaining thing is to finish the integration, right? So now a equals to 2 and b equals to -1. So the integration we are interested in. Okay, actually equals to integration of 2 over x minus 1 dx plus -1 x minus 2 dx. So that's very easy. You have two logarithm term coming off, right? You have log 2 x minus 1 plus minus log x minus 2 plus c, right? That's how you finish a problem like this, okay? So that's kind of a general strategy for you to solve partial fraction techniques. Is you do long division if necessary. If the numerator has a degree larger or equals to the denominator, you have to do long division. Then you apply the partial fraction techniques to the remainder terms. And for that, you have to find the right template according to your factorization. Okay. And then you have to do the solve for the constants, and then you have to do the integrations. Okay. So with that understood, let me do one last example before today's section ends, because we have been talking about 1.5 hours already, and that's a very long time already. So let me end today's section by one last example. which is the example that Dr. Chadwick gave in the worksheet. I think is this one here. Well, let me see. Actually, let me quickly remark the two questions that we have. One is the following. Let me do this actually. 2x plus 5 over x squared plus 3x plus 2. Okay. So this one, there's no need to do the long factorization, the long division, because the denominator is 2 degree 2 and the numerator is degree 1. So you only have to factorize the denominator. So this one actually equals to x plus 1, x plus 2, 2x plus 5. Okay. And to do that, the right template for this one, because you have two linear factors, is going to be a over plus 1 plus b x plus 2. Okay. Okay. So this is the right template, and I will leave the computational constant to you guys. So let me do another finding right template kind of thing. So suppose that you have something like this, x, whatever it is in the numerator. Suppose you have x times x squared plus x plus 1. Then the right template for this one will be a over x plus bx plus c over x squared plus x plus 1. Okay. Suppose you have something like this, x squared plus x plus 1, and you have maybe 7x squared plus 9x plus 11, doesn't matter actually. So the right template for this one, because you actually have a repeated term now, okay, then the right template for this one is a over x plus b over x squared plus, for quadratics, you have cx plus d x squared plus x plus 1. Okay. Remember that this quadratic is irreducible, meaning you cannot further break it into smaller pieces. Okay. So this is the right template for that case. So let me do one more case of finding right templates. So suppose you have x times x squared plus 1 squared, 11x plus 190, for example. I don't know, I don't care about that part actually. So this actually, now you have a repeated expression for the quadratics. What you have is a over x, this is a linear term, so you have a. Because you have a quadratic which is repeated, you have x squared plus 1, bx plus c, you have x squared plus 1 squared, dx plus e, okay? You guys have a feeling, right? Do you guys see how this works in terms of finding the right templates when you have different expressions? I think this is one of the key points you have to be, really understanding the different situations. Okay. So with that said, then the very last thing is how do you integrate something like this? Actually, I think that's pretty much the question, because the questions that he gave in the exam review are very simple because the factorization are very simple. They're all linear pieces. So essentially speaking, you have 3 linear pieces, 2 linear pieces, and you have to solve out constant. So I won't be giving the answer right now for number 5 and 6 on the video, but let me write out something and send it to you guys later. Okay. And from number 1 to 3, which involve trigonometry substitution and trigonometry integrations, I think that's something we reviewed actually before the spring break. Since due to the time limit, I won't be able to give you the details today, but I'll be writing out the solution to you guys, so you can have a feeling how to do those things. Okay, that makes sense?
Hey, Bo, do you think you could do a partial fraction from the worksheet? I couldn't figure out how to solve for the like the A, B, and C for that one.
8.4 to 8.6, you mean?
Sorry?
Oh, which worksheet? The 8.4?
Oh yeah, 8.4 and 8.6.
Okay, let me see.
It was a 3B.
Okay, let me see. If I have it here.
I can tell you too if that's better.
Let me just search my email actually.
Yeah, no problem.
Yeah. So let me see. 8.4 3B you said.
Yeah.
Okay, so let me write down the question. So this will be our last question. It's involving integration x squared minus 4, right? Squared. Dx.
Yep.
Yep.
Yeah.
So in this case, first you notice that you have a factorization for the denominator, which is x minus 2 squared, and the x plus 2 squared, x squared, right?
Mhm.
Dx. So the partial fraction decomposition for this will be a over x minus 2 plus b x minus 2 squared plus c x plus 2 plus d x plus 2 squared, right? Dx.
Yeah.
Okay, that's a red template, and now we have to solve for it. Actually, that's a harder part of the question to me, is to solve for this. So let me do the cross multiplication. So this is a x minus 2 plus b x minus 2 squared plus c x plus 2 plus d x plus 2 squared equals to x squared over blah, 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 okay? So you multiply both sides by the denominator. This gives you a times x minus 2 x plus 2 squared plus b x plus 2 squared plus c x minus 2 squared x plus 2 plus d x minus 2 squared. That makes sense?
Mhm.
Equal to x squared. So we have everything here.
Yeah.
So now how do you find A, B, C, D? I guess, I mean, that's
Yeah.
where I talk about the strategy I've been mentioning to you guys. We use special values first to help us, right? You notice that you have two linear pieces, right?
Mhm.
Whose solution are 2 and the minus 2. So when you have x equals to 2, which term got killed? You got A killed, you got C killed, you got D killed, right?
Yeah.
So that means B times 4 squared equals to 4. Gives you B equals to 1 over 4. Right?
Yeah. Good now.
When x equals to minus 2, which one got killed? So A got killed, B got killed, C got killed, but D is not, right?
Mhm.
So that gives you D times 4 squared equals to 4, and D is 1 over 4. Okay?
Yeah.
So then with these two sides, with these two question answered, so let's see what is 1 over 4 x plus 2 squared plus x minus 2 squared. Then we actually have to solve something then from there. I think that, so then what's the next value I want to pick? I guess, I want to pick maybe x equals to 0, I guess.
Mhm.
If x equals 0, then you get minus 2a times 4, which is minus 8a, plus 4b, plus, again, you have 8c, plus 4d equals 2. When x equals 0 is 0, right?
Yep.
But you know that b and d is 1 over 4, so these two combine to be 2, right? So that gives me that minus 8 plus c equals to minus 1 over 4, I guess. That's my answer. That makes sense?
Yeah.
Let's see. Yeah, I
Wait,
think so. Yeah, right?
what's the last leap there?
Which one?
You have
I plug in x equals 0, and I get minus 8a plus 4b plus 8c plus 4d equals to 0. So I get minus a plus c equals to negative 1 over 4.
and then from there, how do you solve for A
We
and
need
C?
another equation to solve that for sure. Yeah. So I'm thinking about which solution I want to pick further. But another thing we can see is that a plus c actually equals to 0. Do you guys see why?
Wait. So how'd you get the negative 1/4 then?
That's because when x equals 0, when you plug in x equals 0 into the expression I write down here,
Yeah.
you get this expression. And also considering that b equals to 1 over 4 and d equals to 1 over 4. Okay.
Yeah.
Do you guys see why a plus c equals 0? Actually, that's something very, very funny. What's the highest degree on the left-hand side? The highest possible degree is degree 3, right?
Yeah.
For the term involving a and c, you could maximally have x cubed. See that?
Yeah.
For b and d term, you maximally have x squared, right?
Yeah.
But the right side is just x squared, right?
Right.
That means there's no x cubed term appearing from the left-hand side.
Yeah, so they have to cancel each other out.
So they have to cancel out. So that means the a plus c has to be 0 because what's the leading coefficient for x cubed for this term is c, and the leading coefficient for x cubed for this term is a. That makes sense?
Mm-hmm.
So that's why a plus c equals to 0.
Yeah.
So from these two, you can solve for that. So now a equals to, I guess, negative c equals to negative 1/8. A over a equals to actually 1/8, I guess, right?
And how do you know this again? One more
Yeah,
time.
how did you do that last part?
Oh, you mean how do I get from here to the answer, or how do I get a plus c
Right.
equals to 0?
How
the
do you
first
get,
thing.
yeah, from those to the answer?
Oh yeah, what happens when you add these two equations together? You get a canceled out, right? You have 2c equals to negative 1/4.
Would you mind like just writing that just so I can?
Oh, sure, yeah. I mean, so what happens when you add this equation? Let me call this one star, this one double star. What happens when you add these two together? You get
Oh yeah.
Thank you.
negative a plus c equals to negative 1/4 plus 0. So 2c equals to negative 4. So c equals to negative 1/8. Okay, that makes sense?
Yeah.
Yeah,
And then you do
thank you.
once you know c, you know a, right? Because you can plug c into one of the equation and you solve for a. Right?
Mm-hmm.
So that's how you get a, b, c, d. And once you have that, you see that this expression, if you know a, b, c, d, the integration is actually pretty simple. For these two terms, you have logarithm. For these two, you have power rule, right? Substitution and power rule,
Yeah.
right? And then you
Thank
can
you,
solve the
Bo.
problem then. Make sense?
Thank you.
Yeah. Thank you a lot.
Yeah, that's how you solve this problem. So for partial fraction, I want to emphasize again that practice on long division, practice on how do you find a red template according to different expressions. If you have repeated terms, how do you do the red templates? If you don't have repeated terms, how do you write templates according to the degree of the factors? Linear factors, you only have a constant. Quadratic factors, you have a linear piece, which involves two constants, ax plus b. And similarly, going on and on, okay? And suppose you have a degree 5 polynomial in the denominator. How many constants do you expect? You expect 5 constants, always, right? Because when you factorize, no matter which way you do, you always get 5 constants. Suppose you have a degree 3 polynomial in the denominator, you have 3 constants to be computed. You have a degree 4 polynomial, you have 4 constants to be computed. That's always the case, okay? So make sure you double check that you are using the right templates before you solve the equations first.
So the degree of the denominator correlates with how many constants we'll have?
Exactly, that's what I'm saying. The degree of the
Understood.
denominator
Yep.
will be equal
Thank
to
you.
the number of constants you're using.
Thank you.
Yes.
Yeah. Helps.
And once you have that, then do the partial fraction is just do it carefully. And of course, you have to know how to do completion by square, which I don't have the time to explain today. I will leave it to you guys to work on that tomorrow, I guess. Work on that and after class. That makes sense?
Yeah.
Okay,
Are you having discussion on Thursday as well?
Yes, but you guys are having exam tomorrow, right? Or
Yep.
okay, so then I guess I'll having a discussion on Thursday to see what is going on. If we don't have too much to think, I will give you some lectures on what's coming off later on power series and things like
Awesome.
these as a pre-explanation, I guess, to help you guys to get through this for the semester, actually. We need more work, actually. That's the point.
Awesome. Thank you so
Okay,
much.
perfect, perfect. So,
Good luck.
okay, I'll see you guys. Hopefully everything will be good for you tomorrow, and let's see how it goes. Okay,
Thank you so much. All right.
Bye.
See ya.
Have a good one.
you too.